in the middle with just a strip across the top of the screen. That's one way to view, and that's nice if you want to count my eyebrow hairs. But there's a better way to view this screen for socializing. In your upper right-hand corner is a button that looks like that with the word view next to it. And if you click that, you can select gallery view instead of speaker view. And I think you'll find that's a better way. Thanks, Stephanie, for nodding your head. It's always nice to show people that and they go, oh yeah, that's good. So that way you can see more people. If all those wallflowers who are not turning on their cameras, turn on their cameras, it'll be a better screen. No judgment though.
We are up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're up to about 15, 14. That's not bad. And it is 7 o'clock. I will wait, oh gosh, I will wait an entire full minute. But at 7:02, I'm launching. So that's a heads up. So in the next minute and 3 seconds, we are going ahead.
Teaching an online astronomy class right now, and every week, like 2 kids out of 11 turn their video on.
Really?
Oh.
Yeah, it's kind of annoying.
Yeah. Is it that you want all of them to have it on so you can see them?
I would like to, yeah, because I like to be able to see their reactions and stuff. So
yeah, that's why I like. In fact, I like Zoom more than the platforms I was using in the past before COVID, like WebEx, because I mean, in the past it wasn't a platform actually. It was that I was talking to a room full of amateur astronomers with one webcam in the front of the room. This way, if any of you nod off, I'm going to know. You know, we can all see it, and that's okay anyway.
I think that's the problem with nightly Zoom meetings. You got to worry about keeping people on task. All right, my computer just told me it's 7:02:00, so that means I am going to start this meeting. And I'm going to start this meeting by sharing a PowerPoint. Let's see, if I hit that button, and if I hit that button, and then hit that button, I think you're seeing a PowerPoint. At least I hope you are. Tonight's meeting, well, first of all, welcome. This is the October 2020 NightSky45 Zoom meeting, since we don't meet in the college until further notice. But I welcome everybody here. Hope you enjoy this meeting. We have a great speaker, Tom Field. He's going to tell us about spectroscopy, assuming I can say that. But in the meantime, we have basically 5 topics that we hit by the time the meeting is over. The first being the opening remarks. What I guess I wasn't thinking of saying is that I hope you got out this last month. I know it has been pretty awful as far as all that smoke in the sky. I do both planetary and deep sky imaging, and I can tell you that the deep sky was basically a bust. Forget it. I mean, the smoke will really kill you if you need great definition on your faint deep sky objects. On the other hand, the planets are actually pretty forgiving for all of that. And that being the case, it's nice to see that. And so I actually was able to do a little planetary work. So when it comes to the third piece of the observing reports, I'll be able to show at least, I got something done this last month. It wasn't a total bust for me, but it definitely was a struggle. On that note, I'm just going to say that after my opening remarks, now I hope Greg is in the house because he does the Treasury report. And then we'll follow with observing report, and then what's up by Jim Baumgart, who and I saw him enter, so I know that's good. And then we'll finish with the speaker who's going to tell us about you can almost touch the stars. So with that, I'm going to get out of that screen, and that should bring us back to go. Oh, I see somebody's in the waiting room, so I'll bring him in. And I'm looking to see, is Greg? Greg, are you there? I do not see Greg. Okay, then, that being the case, I fill in as the treasurer, and I say just what I know, which isn't very much, to say that In the treasury, last time I reported, I think we had like $1,650-ish. I'm going to say plus or minus 50. If we took in any other member fees, we'll have more, but I don't know that Greg has mentioned that to me. So anyways, that being the case, that is our treasury report. And with one eye looking at seeing who's trying to admit and seeing if Greg shows up, I guess I'm going to have to say that constitutes our treasury report. Oh, and the other thing I forgot to mention, is not to have your phone ringing while you're trying to do this. Sorry about that. I just threw the phone out the door. That helps. While the meeting is going on, and I notice most of you guys are doing it anyways, but it'd be good if you could mute your microphone if you don't have something to say. I know in the past we've had some issues where somebody had it open and they were getting a lot of background noise that they weren't even aware of. And all of a sudden they become the prime speaker. So thank you for muting your microphones during the meeting, unless you got something to add. Okay, that being the case, that's the opening remarks and the treasury report. I guess I'm gonna just head on over to observing reports. Does anybody have any observing reports? And I'm scanning the, doesn't look like it. All right, well, that being, Chris, do you have one?
Oh, just a little bit. Irene and I went out and we looked at Mars. It was nice and bright and red, and saw the actual polar ice cap. That was kind of cool. And then I think you reported that that the space station was going to do a flyby of Jupiter, and we actually went out and saw that too.
Thank you. Chris, what were you using to look at Mars?
I had my 8-inch Schmidt-Cassegrain Meade telescope. So we just did some observing, didn't do any photography or anything.
Nice. All right. Yes, it was interesting. The night that the ISS passed just under Jupiter was supposed to be cloudy, and it turned out it wasn't, at least not from my house, it wasn't, because I saw it and I actually did image it. I imaged it, and I published it, and so somebody may have seen that. Yes, I got it, but it, even when I magnified that single frame, it just looked like a kind of a whitish rectangle. It is the correct general outline, but it just didn't, you didn't look at that and say, yep, that's it, all right.
Yeah.
It had a very bad UFO look to it, I had to admit.
Well, at least you captured it.
Well, it was, I knew it was about a 1 degree under Jupiter, and so I went there and just hoped. And I did catch it, but I had not much magnification on it. So now I know how to do it next time with more magnification. I will get that yet.
Yeah, it's always fun to actually view it in a telescope too. It's remarkable that you can actually see the panels. The panels. It's fairly close. You'd think it would be a lot farther.
Yeah, it's moving fast, so it's kind of a tough capture. It flew right through there.
You have to catch it when it's just coming up over the horizon and follow it as it comes towards you.
All right, is there any other observing reports? Okay, not hearing any. I'm going to show what I imaged this last month. So I'm going to need to share my screen. Let's see, this looks good here. Okay, can everybody see the moon? I hope. Yes, no? Stephanie, yes or no?
Yeah, we can see it.
Yes.
Okay, this was with my C11 Schmidt cast. This was at prime focus, F10. And this is the best 250 of 2,831 frames stacked and aligned and sharpened in the various free softwares that can do that for you. In that image, the crater to the left is Gassendi, and the one just slightly to the right of center is Mersenius. Yeah, that's, yeah. This was done, I should mention, on October 2nd. I'm sorry, on September 29th. October 2nd was full moon. So this is just a couple of days before full moon. So you're only going to see these craters when it's close to full moon, because otherwise they're going to be dark. You won't see them. All right. Next one is the crater in the center, which is not really well defined, is actually John Herschel. And this is at the bottom of the moon, which might be the north side since the telescope inverts. Again, this is another one that's you don't see too often because it's so close to the edge of the moon. And the last one is, this is Schiller. And again, you're only going to see this if it's close to the full moon, because otherwise the moon will cover that up. But it's got kind of a really neat elongation to it, which to me, I'm guessing it's probably two craters that got there about the same time. And so the walls broke down between them. And so you just get this long, skinny oval look to it, ellipse kind of. All right, moving out of the moon, here's my Mars. This was from, says 10/9. Okay, so that would be October 9th. So that wasn't too long ago. I think that was last week. That's definitely Syrtis Major. That's the south polar cap. And Sinus Meridiae is trying to get onto the planet, but we can't see it yet. But not too bad. Mars is about as big as it's going to get. So I think this might be as good as I'm going to get at Mars. This turns out to be the best. This is the best, get this, the best 500 frames out of 10,756 frames. This is with the Canon 60D at movie crop mode, which does 60 frames a second. And I believe this was 3 minutes worth. So that gets you an awful lot of frames. And I thought the more I could get, the better I could go with 500 frames and get some nice stuff. So I was pretty happy with that. Okay, next is Jupiter. Here's Jupiter. This is the best 500 of 2657. And you can see that there is a shadow on the disk. And here, I'm not sure if you can see it, but right above the cursor is the moon that's creating that shadow. So there's a total eclipse of the sun on Jupiter, but of course there's no solid surface, so that's not really good if you're going to be there. And finally, oh, that was the C11 too. And so is this. This is Saturn C11, also on October 9th. And this is the best 1,000 of 5,360 frames stacked, aligned, and sharpened in Registrax and AutoStacker and PIP. All right, so that is my report. Okay. Oh, another attendee. Welcome, James, if you're there. All right, let's see here. Okay. Okay.
I am here.
We will go to our next section, which is What's Up by our own Jim Baumgard. Jim, take it away.
All right, let's see if the screen share works.
I got my fingers crossed.
Whoops, that's my card game. That's not the one I wanted. Sorry about that. This one. Too many things open at once here. Okay, slideshow. Yeah. Okay, can everybody see that? Good. All right, what's up for October 2000? Start with the moon as usual, since that kind of drives most other observing, especially deep sky. Last quarter was on the 9th. I think that, yeah, that was past its history. New moon on the 16th. And that, yeah, 14. I saw it this morning early looking out the window, and it was near Venus. A real thin, beautiful crescent. Mike, you're shaking your head. You must have seen it too. That was spectacular. Through the clouds. It didn't last long. I
don't get up that early.
Yeah, I don't normally, but I'm working like 12-hour days now and getting up at 5 in the morning. This is grueling at my age, especially. Anyway, we have first quarter on the 23rd and full moon on the 31st on Halloween, and that will be a blue moon since we had earlier we had a full moon on the 1st. This is blue moon is defined as the second full moon of any given month. All right, for planets, we have Mercury. It's rising in the east early in the morning in November, and this will be a fairly good time to see it, although it will be morning. Venus is in the east in the morning sky all month, as we know. Mars is visible pretty much all night, and it's still big. It's just past its largest or its closest to the Earth appearance, but it's still displaying around 22 arc second diameter, which is quite good for Mars. So this is still a good month to see it. So get out there and do that. Jupiter and Saturn are right close together in the sky, and they're out all in the evening anyway. They set sometime after midnight. So still a good time to see Jupiter and Saturn. Uranus is up all night, and now it's a good time to observe it. And Neptune's up all night. So this is a really good time for planets. And prime observing is on October 17th. That's the Saturday nearest the full moon. Okay, opposition, or Mars was at opposition on the 13th, which was what, yesterday. So it's still prime observing. And this is the best Mars observing until the year 2035. So for a lot of us, this is our last best chance to see Mars this well. Daylight savings times ends, and I didn't put a date on there. Oh, shame. I had no idea. It's this month sometime. You look at your calendars. I apologize for that.
It's on the 31st, isn't it?
Is it? Let me look here. Not 31st, apparently. I don't know.
I think it's the morning of the 1st of November.
1st of November?
Yeah, 2 a.m.
Basically the night.
Okay.
Yeah.
That's why I'm doing it this October, because it's before the next meeting.
Yeah. So before you go to bed on the 31st.
Okay. And we have a meteor shower this month. It's the Orionids. This is on the morning of the 21st is the peak. There is no moon to interfere, so that works out really well. It's a fairly weak shower, about 15 meteors per hour. But because it's a good, viewing this time without the moon, it's still worth doing. And the radiant is up near Betelgeuse in Orion. Okay. The zodiacal light is still visible in the early morning sky if you have a really dark sky and a good eastern horizon. And that's just before the start of dawn would be the best time to see it. Not that many people have seen it. It is a little hard to observe, and if you got any light pollution at all, because it's so faint, it doesn't hold up well to light pollution. But if you get a chance, give it a try. And happy observing. And that's all I have. Now, how do I get out of stop share? Okay, got it. All righty.
All right, thank you, Jim.
Yep.
All right, we are now ready for our speaker of the night. It's Tom Field, and he's going to tell us a story about you can almost touch the stars, which sounds pretty interesting. It's about spectroscopy, which is definitely a topic we don't hear too much about. So I'm very interested to hear what he has to say. Tom, are you ready?
I guess I am. Get all pumped up and ready to go. I am ready, Mike. Thanks so much for bringing the meeting to this point, and also all of you for inviting me here to speak. So it's after dinner. I'm going to have to keep it a little higher energy than usual, or I'll be hearing the thunk of microphones and seeing the tops of heads as people fade out, and that's okay. It may not be the topic for everybody, or it may just be getting later and later. So I'm going to speak for 45 to 55 minutes, and then we can do Q&A afterwards. Just looking here, it looks like everybody's muted, which is wonderful. Thank you for all doing that, except Nick. Nick, you could mute yourself, or Mike, you could mute him. Put him in the penalty box too. So I lived in Canby for a few years. I'm up in Seattle. I'll tell you a little bit more about how I got into the topic as we get started. Let me just do one thing to get my screen set up, and we'll get things shared and be on our way. There we go. Nick or Mike, somebody, Mike probably, can you see that prism there? You can just shake your head yes. Great, thanks so much. Let me just get a little bit more setup done here. Oh, that looks good. Nice turnout, thanks again. So how have we managed to discover so much about the universe when, we really haven't even left home? We can see images. Of course, we've been capturing those for ages to look at the night skies, and we can get a fleeting glimpse of third dimension during eclipses, of which you had some good opportunities to do that a few years ago. If we wait for a while, the fourth dimension, time, comes into play, and we can see stars changing in intensity. Up in the upper right-hand corner, you can see one. Frankly, years ago, I could have looked at this changing like this, and just all the stars that were blinking on and off would have become very evident to me. But to be honest, these days, sometimes I have trouble, even looking at the center of it right now. I find my averted vision, my peripheral vision doesn't track as well. Things can pop up on a second monitor, and I won't even notice them. But these are RR Lyrays. They're standard candles. There's one of them going on and off in the upper right-hand corner if you haven't spotted one. If we spread the colors out, we get this, as if fifth dimension. This is beautiful, isn't it? Just aesthetically, the colors are just gorgeous, the way they slowly transition through the different shades. And those all those gaps in there are a result of the spectrum. And we're going to talk about those tonight because they can reveal a lot of information about a star, its composition, and lots of other things. I'm not going to call off these bullets, but you'll hear about them as we continue on. I'll give you some examples of these things and how they work. So I realized over the years that I wanted to convey certain points, and rather than just sliding them in, I just lay them out. Here's what I'm going to say tonight, and here's what I'd like you to hear anyway. So whether you're a imager or not, whether you're maybe even an armchair astronomer and don't even get up to a telescope, although I seem to remember seeing on your about page for your site that you're about active or observing. I forget what the words were for your group, but so most of you may have telescopes, which isn't uncommon, of course, in these. Maybe you're not imagers, but I was a pretty bad imager years ago, and but even further back than a few years, a couple decades ago, 2-3 decades. It may have been the same for you. When I captured my first image, it was the moon. It was blurry, it was overexposed. It was still the most beautiful image I'd ever seen of the moon. I took it to all my friends and my co-workers and my wife, and they all, at some point, they just said enough, because I'd bring in a new blurry image each morning. But that thrill, of course, fades in time. And what I found is that spectroscopy rekindled that thrill. You might want to do some science with your equipment in addition to the visual imaging that you're doing. And this is an opportunity to do that. Maybe you don't want to, like most of us, don't want to take the risk of big investment until you're interested in it, or never. And I'll show you some really inexpensive ways that you can do things. I think this is, to me, the most significant point in my talk. And that is when, as you know, if you've imaged, when you own the data, you have a totally different relationship to it. You're curious about it. You read about it. And better yet, you actually remember the things you read. So that to me has really been significant in terms of what spectroscopy has brought to my life. You don't have to drive to a dark sky site. Unlike visual imaging, where as you get deeper and deeper into it, especially when you're stacking images, as we saw some nice examples earlier, this isn't the kind of thing where you want to do a lot of tweaking of your image afterwards. You want the photons to be on your sensor and then be used as data, pretty much the way they showed up at your telescope. So, and for me, that's great because, you know, I've never shown this example before, but, you know, there was a book years ago that was a large format book like this. And it was like Photoshop for astronomers. And on the left page, let's see, this would be your left. On the left page was the before image, and then they'd have a whole bunch of text on, and then they'd show the after image. And I'd look at those two and I go, yeah, I guess there's a difference. But is that really worth the time I spent reading that paragraph? It just wasn't my thing. But the good news is you don't have to get into those kinds of subtleties when you're doing spectroscopy. You don't have to have a PhD in astrophysics. I don't have an undergraduate degree in science, for example. I'm going to sound like I know what I'm talking about tonight. And this is not false humility. I really don't. I'm like that broad river that's really shallow. And that's okay. There's no tests, there's no exams. And I'll point out some things tonight to reiterate that. I'll tell you some things and then say, this is all I know, literally all I know about this topic. Who cares? You know? We're adults. There's no quizzes. We don't have anybody giving us exams. I was a terrible imager. I'm glad there are some really great imagers out there, but I'm not one of them. Listen, you look at, I used to do this in my talks. I go to the back of a magazine. Actually, in person talks, it's really fun because you can just ask somebody in the audience. And unless you've placed somebody in the audience like a magician with a shill, it's a person you've never met, right? And you can ask, you ask, does anybody have a magazine, a Sky and Telescope or Astronomy or something? Oh yeah. So you ask them to, just open up to that featured images section in the back, and you see some, gorgeous image like that one. And then you ask them to read the fine print. And it says that it was 45 hours of integration time. Listen, and I know you can, it's not often I get to say this line with people actually understanding where I'm coming from. I don't get 45 hours of clear skies in a month in Seattle sometimes. So that's not for me. And that's okay, because I'm going to show you things tonight that you can do with a video camera with just one frame, literally. I break just about every piece of equipment I touch. My wife won't let me fix things around the house, and she's wise to do that. I think edit, undo, Control Z in Windows is probably my favorite keystroke. And I'm going to show you things. You don't have to build up a whole complex rig, really simple. If you do outreach, and I know the club does, I know that area of the country, you do a lot. I just follow a little bit of it. What's that? You can tell me after the talk. It's something like 3R Observatory or something that's down there. That's down in Medford. That's a little further south than you. But if you do outreach, I'll show you some screens that really can augment the outreach you're doing. And if you want to mentor, this is a fantastic opportunity for that. Because instead of going into a school and going, yeah, I'm going to show Johnny or Jill how to, what are you going to say? What are you going to do? Like size of craters or photometry, which in my case never really captured my interest. But with this, you can go in and say, your student, if they're qualified and we have enough, clear nights, they're going to, detect and measure the temperature of a star, or it's 25 light years away. Mentoring is really a wonderful activity, and of course the primary reason is you want to hang out with a cool crowd. That's not me, I assure you, but there are thousands of people doing this, so you're not really on the bleeding edge. Okay, I promise you that's the most number of words you'll see on one screen. Forgive me for that, but that just sort of gives you the flavor of what I want to communicate tonight. And I want to get into a little bit of the science. Let's first of all get everybody to approximately the same level. Sir Isaac Newton, of course, split white light in a prism and was able to see a rainbow. You can do the same thing by bouncing light off a finely lined surface like that DVD, or by passing it through a piece of glass that has finely grooved lines, say a piece of glass that has 100 lines per millimeter, to give you an idea how fine we're talking. Bunsen invented the Bunsen burner to burn a sample. He passed the light through a prism and then he observed it here, and he saw lots of unique spectral lines for different elements. The cool thing was he was a real pyromaniac. He burned everything. He kept great catalogs, and they really served astronomers in the decades and centuries to come. Kirchhoff over here, we won't talk very much about it. He was a contemporary of Bunsen's. But before I mention him, I just want to mention one cool thing about the Bunsen burner is Bunsen deliberately didn't patent it. He said, I want this available for the, the benefit of humanity going forward. Of course, today there'd be 10 patents on, on each screw and on the angle that the pipe was, bent coming off of it. But to come back to Kirchhoff, one quick thing, I'm not going to spend a lot of time on this slide, except to point out that when you get a spectrum from a star or other objects, it can be the Roy G. Biv rainbow with just some gaps, or it can be a black background with some lines. Now, which one you get depends on, let's come over here for a second, on the temperature of the gases involved and so forth. We're not going to talk about that. That was Kirchhoff's thing. But what I wanted to point out over here was that the line that you get, whether it's the emission line or absorption line, and you think I'd hit the right button, having given this talk so many times, is going to be in the same position as the other.
I'm having trouble hearing you.
Yeah, Siri's complaining. I guess I'm yelling too much. So that's all I wanted to show you. I'll show you examples of both of these as we go forward. I'm moving quick because we got a lot to cover tonight. Hydrogen has a line there that, look, helium doesn't. These really are as if fingerprints. And hydrogen is so common in the universe and so frequently used that we've given the series of lines in hydrogen names. Alpha, beta, and gamma, for example. So the alpha's in red, this beta is, it's about robin egg blue, and then gamma. And here very quickly is a periodic table of spectra that I created some years ago. We sell it mostly to educators. You can see on the hydrogen, there's the red alpha and robin egg blue beta. Notice how those lines are very different than, say, the helium lines here, or even, for example, these lithium lines. These would be from, if I was foolish enough to burn a lithium battery from my cell phone or laptop, that's what the lines would look like if I survived the experience. So they are fingerprints. These days, we don't have to burn things. Unlike Bunsen, we can use gas tubes. Here's a gas tube here. Let's make sure you can see it. You can. This is a helium gas tube. And they're just, it's like a fluorescent lamp. It's got a gas sealed in a tube. So let's come back here. This is actually hydrogen in this gas tube. And you can see there's a hydrogen alpha in red, and there's the robin egg blue beta, for example. I created a few years ago this camera that educators use on gas tubes, in front of their classroom, because teaching spectroscopy has always been a challenge with these little handheld spectrometers and grading foil. These can really change things. We have a lot of these out in the field, both at the university level, as in lots of high schools, community colleges. It's a cool product. Same software. Same exact software. So in 1835, jumping around a little bit, this French philosopher said the stars are too freaking far away. And I had to practice that expression in the shower this morning. But less than a few decades later, all these astronomers were, I was going to say amateurs. It's hard. Back then, they were both amateurs and pros sometimes. But they were observing stars and seeing something about their composition. So, science changes in just a few decades. Sometimes I wonder 2 or 3 decades down the road here, what we'll know that today we don't know at all. Will it be in life sciences? It could be anything. I'm going to just take a moment here to tell PowerPoint that's a feature that should have been changed about 30 years ago. So you could set a default permanently. You still have to do it, as far as I know, every time you want it. So far, everybody I've talked about are what? Old white men. So let's look at some examples of women in the field. Annie Jump Cannon and her team from a little more than 100 years ago were prohibited from accessing the telescopes at Harvard because of their gender. So what they ended up doing was observing the glass plate spectrofilms. They were great at it. They classified hundreds of thousands of stars. And with that much data, they began to see patterns. They did a brilliant job of figuring out a way to classify stars that basically was the right way, as opposed to all the preceding ways that had been developed by men. But more importantly, I don't mean to throw men under the bus too much, but more importantly, they came up with this classification system that served us going forward in time really well. So Priyamvada Natharaja is at Yale. She studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD as a woman in the late 1940s, a remarkable accomplishment. That's the Hubble Space Telescope behind her, which she was a huge proponent of. Elisa Quintana, she studies exoplanets and has discovered some around red giants that may harbor water. And Jedediah Eisler's at Dartmouth, and she studies the gravitational lensing around black holes. So we've come a somewhat long ways over the past several decades, although we have a long way to go. And fortunately, changes are happening. So a little more science. How do we get absorption and emission lines? Well, Niels Bohr model of the atom that we can use here for discussion's sake, you may recall has these orbits where an electron is, let's get back onto that slide, where an electron is orbiting in different numbered shells. When the electrons drop, having been pumped up maybe to that shell to then drop, they can give off energy, which sometimes is in the visual light range and can be seen. Different drops from different levels down to level 2 give us different colors. So for example, just quickly, this one here drops from level 4 to level 2, and that means that it gives off energy in, well, the robin egg blue. This is our hydrogen beta. So what happens when an electron jumps up? Because they have to get pumped up to level 4 before they drop. Well, in that case, we get this absorption spectrum with the continuum in the background and a gap. We'll see examples of these both as we go forward. Here's the Hubble Space Telegraph. That's great. Space spectroscope. And the space shuttle is servicing it. My teenage grandson looks at this and he says, you know, he knows better, but he says, this is a refrigerator and it's not a scientific instrument and it's filled with beer. And then he says at night on the space shuttle, when it, you know, they were party animals when they were in downtime, and you get a lot of nights when you're going around the Earth as often in 24 hours as you are on the space shuttle. We need not get more deeply into that. Here's a really complicated setup by a friend, Dale Mace. I think he may, over the years, have regretted giving me permission to use this image. Look at that rat's nest. But it doesn't have to be that complicated. I'm going to spend a lot of time tonight showing you examples from a star analyzer grating. You can see here, it's an 1.25 inch filter cell. It's durable. It's got glass on both sides. Doesn't matter. In fact, it's really, I have never mentioned this tonight until tonight, but if you look closely, I don't know if you can see it. No, you can't with this setup, but you know, there was one day when I looked at my grating down here and I went, God, it's just covered with spots. And I couldn't figure it out. And then I realized this was my speaker's grating. And so I'm spitting all over it day after day. They clean up easily. They used to say that about some of us, but then the years got ahead of us, didn't they? So it's about $200. Here's a cool example of one in use. The simplest example of usage. It's on the lens cap threads of a DSLR. And in just 30 seconds on Vega, we got hydrogen alpha. There's that robin egg blue hydrogen beta. Notice this doesn't even have any tracking. So it's not a really easy way to go about this. I mean, imagine even just finding a star and keeping it in the eyepiece or in the viewfinder of your camera for 30 seconds. But the reason I like to show this is because, well, first of all, it is a cheap way to get started. I keep hoping I could find some cheap way to, you know, some inexpensive mount so I could say to high school teachers all over the country, here's a cool project, give it to your students you think could handle it, and they can go steal their parents' DSLR and do some cool stuff. But it's just too, I've tried it on our deck here in Seattle, and just even finding Vega, I mean, it's a chat, and then it's moving the whole time. So then you have to move on and do whatever else you do with this. So it's not a good way to go about things, but it is possible. Here's some ways that the grating can be used. We saw this in the previous slide. The reason I wanted to show it here is we do sell this adapter for like 40 bucks that adapts these lens cap threads to 1.25 inch. This is actually something that people who are more experienced and do other approaches use because the light goes through the grating first before the lens. So here it goes through the grating. It's already in a converging pattern. Here the light's parallel, so you can get some really interesting and good results. So here is a Fitz camera, color, mono, doesn't matter, although mono is more sensitive. This is, let's see, this is the ZWO 178, and it's a color camera, which I prefer because it's more intuitive as to what people are seeing when I'm doing outreach and education. And this is an image that doesn't show the grating, but it is in their promise, Scout's honor, it's in there in the filter cell. So there's lots of ways to mount this thing. There are more expensive approaches, slit devices that have higher resolution. I'll show you a few examples of those, but you can see they're an order of magnitude more expensive and also considerably more, I don't know how we measure difficulty, but it's considerably more difficult to use because you're dealing with a 10 or 20 micron slit. And that's how you get the increased resolution, but it also means that you're guiding and acquiring through a really, really small slit. There are ways to avoid that. Nobody starts with these. Almost nobody starts with these. There are less expensive devices that you can print yourself if you're into 3D printing. The plans are available. But again, the same difficulty exists in terms of learning curve. You can piggyback on the back of your standard telescope, so you've got tracking available and you can do something else down here at the same time. Okay, we raced through that. Thanks for your patience. How do we get to be 7:40 at night? We're going to have to race here. So Starlight goes through a grading. We get a spectrum. It falls on our sensor. Here's our first example. I love this because I mentioned you saw on one of those bulleted points we can measure star temperature. These are the stars, all different spectra captured at different times by Torsten Hansen with a 8-inch Newtonian and an imaging source, a video camera. And they're in temperature order. So the hot stars are here and the cool stars, type M stars, are here. So it goes from hot to cool. And those are in Obia fine G kiss me order. And I meant to print this out. I hate that acronym. I don't know if I hate it, but I dislike using it. In these times, I wanted something gender neutral. And the one I came up with, and looking at the audience here, I think maybe many of you will appreciate this. Okay, boomer, a fully green kilowatt matters. It's a mouthful, but it's got the letters of the stars in temperature order. So, but look at the differences here. We'll look at two really quickly. Notice down here, these wide bands, that's like a forest, right? They aren't even lines. You don't see those bands in this position up here. Well, that on these cool type M stars is from a more complex molecule than just a hydrogen or a helium. It's from titanium oxide. And this is one of those places where I can say, I don't know anything else about titanium oxide, except that it's a complex molecule that shows up in bands on cool type M stars. The other thing I wanted to show you is notice how this feature, and that's, let's see, that's, wrong key. That is wrong key. I'm reminded of Rocky and his friends when Bullwinkle would pull the wrong thing and go, oops, wrong sleeve out of his sleeve. So what I wanted to show you was this region here. I got the wrong key again. In about the 4800 region, in, well, the robin egg blue, that's our hydrogen bomber, beta. And this feature is more pronounced. Why would that be? Well, this type A star, like Vega or Alpha Lyra, is the perfect temperature. Remember that these absorption lines, and this is, I promised myself the last night I'll hand draw these on this slide, are when the electron jumps down from level 4 to level 2. Well, these stars are a little hot. So the electrons, when they're getting pumped up, actually pass 4 and maybe go to 5 or even out into the galaxy, into the void. So these hot stars don't have as many electrons starting at level 4 to drop down. These cooler stars have either some electrons. What's happening is some of the electrons get pumped up to 4, but a lot of them just go up to level 3 and then drop down. So you can actually tell the star temperature by looking at these features. It's pretty cool, huh? Now, my wife insists that I dress for success, and I think this is probably the slide to be doing it in. So, you know, if you look down, let's see, where is it? Down here, there's our hydrogen beta down there. But, you know, we're all about color, right, in spectroscopy. And the problem I have, and I'm thinking that some of you at home may have experienced the same thing in your household, and that is deep down here, the color goes to gray. And my salon's not answering the phone. I don't understand. I haven't been able to get this worked on in a long time. So I just have to deal with it. But again, this is a great demonstration of spectroscopy in the field. My wife actually does say dress for success, but those years are pretty much behind me. And so she doesn't literally beg me, but she begs me not to wear this. Whether you're laughing at me or with me, either way, a smile or a laugh, and I saw some there, is nice. I suppose it releases dopamine or something and makes you a little wider awake and more receptive. So you see that crosshairs there? Maybe you see in the robin egg blue, there's a little dimming. I'm actually not quite sure whether that's just dirt on my monitor or not. But if I was to, suppose I captured a spectrum like this and I published a paper, it was from the Hubble, published a paper, in the robin egg blue, we, saw this little dimming, maybe. It wouldn't get published, of course. We need quantifiable data. So what we do is we plot the intensity of that region, and it looks like that, right? The star's really bright, so this is really tall and narrow because the star's narrow. This thing's really wide, so this is really wide, and it's dim here, and then gets brighter, 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 and dimmer, dimmer, dimmer. So again, what we're going to see is it's dim, gets brighter, brighter, brighter as we go up here, and then it's going to get dimmer, dimmer, dimmer as we go down. So, but the really cool thing is now we can see that dip really clearly. Now we're doing science, because now we can measure the full width half maximum, the width of that dip. Where is it located? How does it compare to other stars, other objects, other people's data, other nights? So how do we get that graph? So my story is I wanted to do some science. I got a grading in 2009, went out in my backyard, which is right out the window here in the backyard, 3 miles from Pike Place Market. Set my C8 up. I had a clunky, actually I found it while I was cleaning the basement today. It was like coming across a dear friend. This was it. This was my first camera. And I don't know who makes it, but notice it's curved, right? So I had to take like the end of an eyepiece off and get it on. You can see there some of the duct tape remains. Really, this is an exclusive. I've never shown this before. Came in at midnight having observed Vega. Of course, my blue jeans, the knees were stained because it's Vega in August. What do you expect? Sunday morning, I tried to create this curve and I gave up. I was using freeware that was out there and it was really frustrating. It was crashing. It was hard to even get installed. Half of it was in French. There was no manual and it just wasn't up to the usability standards that we've become accustomed to. So I told my wife I'm supposed to be having fun. This is a hobby and I'm really just frustrated and angry. So I put it in the drawer. I threw it in the drawer. Life's too short to suffer, right? In that way, by choice. But it kept bugging me. So one week during the lunch break from work, I said, Saturday I'm going to write the software. I've been writing software since the mid 60s, not 50s, but 60s. Longevity doesn't mean expertise. I'm a great example of that. But so Saturday, I wrote the software. I had it done Sunday, and this is a plot, and then this is my original data. And now, 10 or 15,000 hours of programming time later, it's almost done. My wife keeps saying, would you finish it so we can start having dinner at the same time in a decent hour every night? Only joking. It's been done for a long time. But one of the obstacles getting started in a new field like this is, oh no, another learning curve I've got to climb, right? Another software package I've got to understand and, learn. And actually, I've heard that, and some of you I'd like to hear afterwards, I've heard that Prism software is fantastic, but that the learning curve is quite steep and long. But I wanted to show you my software just for the spectroscopy piece, because I want you to appreciate how easy these things can be. So this is a single frame from that video from the first night of Vega. There's the star. There's some gaps in the spectrum. There's a really deep gap. So all we do is bracket in the area we want to study, and we've got a spectrum. Boy, what an awful screen. I was doing something else earlier. Let me just restore the color layout. That's a little easier to see, I think. So this peak is the star, and this data is the spectrum, and that dip there is that deep dip. Okay, so what? We've now captured a spectrum. What are all those dips? Remember, I mentioned Bunsen created a catalog, and the great-great-great-great-grandchild of that catalog these days can be embedded in software. So I select Hydrogen Bomber and say, show me over here what the hydrogen bomber lines would look like. And boy, I really left my machine in a sad state. So let me see whether I can, this is really embarrassing. There we go. So we pop up that catalog, and the hydrogen bomber lines are now overlaid on top of my red data. And so here's where the hydrogen alpha dip would be. Here's where the hydrogen beta dip would be. And look, we have a lot of matches. So what we've just done here is with a backyard telescope and a video camera, fairly conclusively shown that this data is indicating that Vega is, at least in some way, involved with hydrogen, and that hydrogen is creating these dips. Pretty amazing with a backyard telescope. We can, for eye candy, colorize that. And the other cool thing we can do, this is actually a recording at about 2 frames a second of that first night out. Let's play the video. So there's a video playing. Things are jumping around here from seeing. You can see the data jumping around a little bit. And this is a fantastic screen if you're doing outreach or education, because it's interesting. People want to know what it's all about. And people, many people, depending on the educational level of the community you're speaking to, will remember and actually say, wasn't that in like one of the early Cosmos series with Neil deGrasse Tyson? And it was. So the other really interesting thing to look at, let's just zoom in on this hydrogen alpha. You can see it comes and goes, it's moving around. Sometimes it's visible, sometimes it's not. Let's turn on stacking, which all of us, many of us are familiar with. Over the course of about 10 frames at 2 frames per second, that feature stabilizes, becomes symmetrical, and becomes a little bit Gaussian. Isn't that cool? It's a nice demonstration of what happens with stacking. So that's all I'm going to show you in the software. What I would like you to do, if you would, is just in your mind's eye, remember that view with, again, those are the hydrogen bomber features, and that's hydrogen alpha, beta, and gamma called out, because I'm going to show you in a few minutes some science that was done with that kind of layout. So let's get back into the show here. There we go. Here's an outreach session. They started with a gas tube here and then transitioned into astronomical object. You wouldn't want to do this at a dark sky site with all that light, but it's, again, great for public sessions. This is actually in Marseille, France. Here's a view from a DSLR with a wide field. Let me tell Outlook or PowerPoint again to leave my mouse visible. So there's 3 stars here. There's 3 spectra here with some gaps. Down here is a star, and here are some lumps, right? So those are emission lines that, you know, saturated our pixels. But in fact, let's look at a Wolf-Rayet star here. So when Janet sent me this, I have a confession to make. I couldn't remember what a Wolf-Rayet star was. You know, I'd read about them lots of times over the 30 years that I've been doing this stuff, been doing astronomy. But you know, things do go in one ear and out the other. Well, Wikipedia is our friend. Wolf-Rayet stars are, you know, 25 times more massive than our sun. They're late stage. They're probably going to be a supernova. They've got intense stellar winds. So some of the outer atmosphere is dissipating. And here's what the spectrum looks like. Emission lines for carbon, carbon, carbon. Why would that be? Well, remember, stars burn through the elements step by step, from hydrogen to helium. And so we're actually seeing one of those steps in the star. It's remarkable that we can see that. These are very broad features because of the intense stellar winds. So this is the kind of thing you may, you know, get into Wolf-Rayet stars and image the dozens and dozens that exist. And there's several types of Wolf-Rayet stars. There's lots of research. This is just one little area of specialty, which if it catches your attention, you can get into. So here's another emission object. This is an extended object, right? It's not a point source. So we see the object repeated across the field of view. Again, we can see the hydrogen alpha and the hydrogen and the ionized oxygen. That's what that Roman numeral 3 means. That just some of the electrons have been pulled out of the orbits. Most extended objects like the moon or Saturn don't really work well without a slit. You need one of those expensive devices. But let's look at an extended object with a slit spectrometer, the Orion Nebula. Same lines, right? Hydrogen alpha, and there's the ionized oxygen with the 3 Roman numerals, but look how narrow these are and how much other detail there is. That's because we've got the slit. So just for a moment, in fact, I'm going to stop my screen sharing. It would be fun as a group to see this. Just for a moment, I'm going to stop screen sharing. Maybe one of you would unmute your mic, and if not, that's okay too. I'm not going to call anybody. And share with us the first time that you saw the Orion Nebula. Where were you? What was the telescope? What was your experience? What did it look like? Any volunteers for that? Anybody want to share their experience? And that's okay if you don't feel like you want to jump forward and do that. We all have different experiences about that. And since we don't have any takers, I'll share my screen again and just real briefly tell you my story. And that is that I was in the early 90s, wanted to see Shoemaker Levy 9, never had a telescope, went in Denver to a first quarter star party. And it was in the city. I walked out on the observing field. You know when you remember when you didn't know something? Well, that was my experience. Here's what the observing field looked like. This is your observing field at one point from your website. But what I saw on the observing field, to my inexperienced eye, you know those cannons that they shoot people out of at the circus? That's what I thought these were. And I'm going, what's going on here? You know, this is cognitive dissonance here. I'm not here to see cannons shooting people. Of course, they were Dobbs. So I queued up at a Dobb being run by somebody much like many of you or me. And I was all excited. They were excited. And I got up to the eyepiece and looking at M42, I was really disappointed, quite honestly. It was a smudge. It was nothing. It was mono. It didn't look like any of the images that I'd seen of M42. But I'll tell you, I still go back and look at the Orion Nebula. This gets hot after a while. I bet if you had a similarly disappointing story, you still go back and look at M42. What's changed? Why would we go back if it was so disappointing the first time? Well, first of all, our equipment's better. We might be in a dark sky site. Secondly, we know how to use averted vision now, so we're able to observe stars, through our the side of our vision where we're a little bit more sensitive to dim light. But I think really, in all seriousness, the reason we go back, and you've seen this in other observing that you've done, the more you understand what you're looking at, the more interesting it is. And so now that we really understand that this is a stellar nursery, the birthplace of stars, it gets much more interesting. And that's what spectroscopy has done for me. So here is the spectra of Uranus and Neptune. You can see these deep, well, they're the dips there, these gaps, right? They are these forests of lines from a complex molecule. In this case, we're seeing the atmosphere. We're seeing the methane on these planets. It's amazing we can do that. So in 1881, Henry Draper observed the spectrum of a comet, and it was significant enough that the New York Times published something about that. Hey, if Hank can do it, so can we. There's the spectrum that we observed, and you can see that beautiful string of gems. There is the profile intensity graph of the swan bands, mostly carbon. This was captured by Vikram Agnihotri. He's a nuclear power plant in Northwest India. He was a beginner in 2013. He's now really advanced. I learned lots of things from him. What any teacher wants is that to happen, that the student becomes the teacher. So here's a more contemporary spectrum done with what's called an objective grading, which means the grading is just on the lens cap threads, as I showed you earlier. So this is a really simple way to observe objects, and this is the sodium that we're seeing in the tail of the comet. So anybody who uses a C-clamp in their setup, that's my kind of amateur. Except it was me, I'd be cranking down that C-clamp and I'd collapse, I'd buckle the housing and destroy the camera. Fortunately, Robin Ledbeater didn't. As a designer of the Star Analyzer, and he's a great guy. He's on our forum. He helps lots of people, including me all the time. A real expert and a real gentleman. He screwed a Star Analyzer onto the nose piece of the camera, and down here is a single frame of a Perseid. So in this much time in one frame, the Perseid, which is that thing, traveled that distance. This is the spectrum here. For example, that gap is that dip. And you can see he was able to identify some of the features. This is, again, not easy. You've got to wait to see the comet. You've got, or the comet, yeah, the meteor. You need to make sure it's in your field of view. There's lots of challenges, but some people get into this kind of stuff. If it floats your boat, why not? I'm not going to talk but an instant about the sun and helium we discovered on the sun. That's something you can do. Maybe you did it a couple of years ago or know some people who did it. I think Richard Berry got some really nice spectra. If you've got a DSLR even, you can observe that some novae have iron absorption lines and others don't. A quick review of Doppler shift. If we or something are moving towards one another, the sound that it emits or the light that it emits gets higher pitched and stretched out as if lower. So for example, a train whistle going through a station, right, high, low as it comes towards you and away from you. You can even observe that from your car. Just when you're driving, if you're going by parked cars or trees, you'll hear that shoo, 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 that swishing as you go by. Suppose we were expecting a triplet to appear right there in the spectrum and it appeared there. What would that tell us? Well, that would tell us, well, it's red shifted, right? It's moving towards the red and it's moving away from us. Or if it's moved to the other side than what we expected, that's blue shift, and that means it's moving towards us. Here's a great example. Particular type of supernovae, type 1a, we're not going to get into a lot of details, except a large star ends up having some of its gas end up on a small white dwarf. And when you pour gas on a hot surface, you get an explosion. Here's a supernova in M101. Maybe some of you observed it some years back. There's an image of a different type 1a, but same type supernova. And notice it sort of looks like a sphere there. And David Strange captured the spectrum of M101. And he was able to, down here, in 30 seconds, or with less than 15 minutes of integration time and a 9-inch telescope, and our star analyzer was able to capture a spectrum. And there's a really deep dip. Now they say, and they're right, of course, as you know, we stand on the shoulders of giants. So this dip here is what the giants use to determine at around 6,000 that this is a type 1a supernova, that binary star. This won't be on the quiz later tonight, and there won't be one, but you can see type 1a supernovae have this deep dip in silicon, and it's down around 6,000. So this is the way David Strange was able to identify this as a type 1a supernova, which is a task that amateurs are called upon to do. Unfortunately, supernovae are fairly dim. Of course, they're in other galaxies almost all the time. And but it is an activity that amateurs do as a part of the Pro-Am collaboration effort. So David and I measured the wavelength on that x-axis there at 6150. And then we looked up what, if Bunsen had burned beach sand, he would have found the same stuff, that wavelength of that deep dip at 6355. The difference of those is from Doppler shift. I couldn't remember the Doppler shift formula, but fortunately, Wikipedia again is your friend and the math is simple. We were able to measure the blue shift from the expanding shell of that supernova as it came towards us. Pretty amazing that we can do that, isn't it? So Adam Rees won the Nobel Prize in 2011 for work that he and his team did before the turn of the century. You may be familiar with that work. It was measuring the accelerating cosmological expansion, and he used type 1a supernovae as a standard candle. Somehow I think he used something a little more complex than our star analyzer grading. But bang for your buck, you know, if I put that formula up there, right, bang underscore buck, then we're getting a lot of bang for a really little buck compared to his multi-million-dollar telescopes. What about the spectrum of a black hole? Well, of course, a black hole doesn't emit light, but the accretion disk, as material spirals in, it gets very hot and emits light. So David Hayworth, who maybe you know, frankly, I'm not sure he's still living. He was quite ill in the last year or so. I haven't been able to get a hold of him. Great guy. He captured the spectrum of 3C273, which I've never observed myself. There's the spectrum, 2 dots of light. There they are there, blown up, and there's the spectrum. So Martin Schmidt was 25-ish years old in the early 1960s, and he studied this spectrum. The reason I know all this is because there's a wonderful transcript of an interview with him where he describes the whole experience, and it's fascinating. There's a link to it on my site. I can send you the link if you can't find it. There's a contact form on our site too. So he was really frustrated. He couldn't figure out what those peaks were. Notice, interestingly, we can't even see them visually here, but they clearly show up in the profile intensity graph. So he decided, okay, I'm going to go back to square one. And what he decided to do was, he, like we do in a lot of science, you know, rule out certain things. Let's just rule out that it can be, well, in this case, he said, let's start with hydrogen. And so he brought up some reference lines for hydrogen. This is the screen of my software I asked you to keep in your mind's eye. See the emission line, or see the reference lines there, hydrogen alpha, there's the hydrogen beta in the robin egg blue. And he looked at these and he said, well, they don't line up at all. So, you know, at least we know it, you know, it's not hydrogen. I wonder what else it could be, except it was hydrogen. And he figured it out. Massively redshifted, which means this object is really barreling away from us. In fact, using the Hubble constant, he was able to figure out that this object was 2.5 billion light years away. The excitement of this discovery wasn't that it was that far away, but that it was so darned bright. Even though it was that far away, we could still see it. And so what's amazing to me is that this light, that old and that far away, having traveled that long distance, still has information in it that we can extract with such simple gear that tells us something about that long changed object. It's amazing. It's as if the light didn't age. Now, other things in the universe do age a little more noticeably. This is Martin Schmidt a few years ago, and I've been justly accused of throwing rocks in a glass house when I showed this image. And it's true, I'm a little envious of him. You know, he's got a full head of hair. I've got none. So 2 more quick examples to show you, and then we'll finish up. Suppose we wanted to look at more detail of these hydrogen dips. Well, how wide are they? If we just drop a line here, oh God, I need a straight line, please. If we drop a line from the edges of this, we can see that, you know, it's about, let's see, these are 20, 40, 60, 80, 100. Okay, so it's, you know, 20 or 30 angstroms across. So maybe we can do a little better than 50 angstroms, but not much. If we want to drill in and look at the details of this hydrogen alpha feature, we can't just use a gradient. We can't use our roller wheel or our mouse and zoom in. You know, it's like when you're looking at the moon and you want to see more details in a crater. You can't just keep adding magnification with higher mag eyepieces. Eventually, you're into empty magnification. There's no more data there to be had. Same thing with this. This is where you need one of those expensive slit spectrometers. There's an example of Vega in fuchsia and in blue the moon. The moon isn't really moving appreciably towards or away from us, but Vega sure is. Look at the difference there. So this is the hydrogen alpha feature there. So you can see we've really zoomed in on it with better equipment. And we can see that what the difference here is 0.67 angstroms. We'd never be able to see 0.67 at this scale. And we were able to determine the radial velocity of Vega pretty close to the published value. Pretty cool, huh? This is with a slit spectrometer. Last example of the night. It's a fast rotating star. I wish I was a Harlem Globetrotter. I can't even hold it and could spin it on my finger. So this edge is coming towards you really quickly because it's fast rotation. So the light coming off this edge is blue shifted. And this light here, as this edge is moving away from you, is red shifted, right? Because it's spinning. And in here, there's not a lot of shift from rotation. So what does that cause the light that hits our spectrometer to do? Well, some of it that is here gets spread out here and into the red or blue, and some of it gets spread out over into this area. So here's what it looks like. There it is. Rotationally broadened spectrum. Now, Vega clearly isn't spinning as fast as Altair because Altair is broadened. Talk about standing on the shoulders of giants, and these giants, we're talking giants intellectually, right? Isn't it amazing what we can do? Who would have thought that with just a simple piece of equipment, we could determine the broadening of a star from its rotation? So how do you get started real quickly here? You need a grating for about $200. You need some sort of camera. If you've got a camera, it will almost definitely work. Big aperture actually becomes a little bit of a drawback. Something bigger than 8 or 9 inches, you'll need a focal reducer just because the star size on your sensor affects the resolution unless you have a slit. You may need an adapter of some sort or a spacer because the distance from the grating to the sensor isn't critical like focus, but you don't want it too far away or too close. And there's a calculator on our site to figure that out. And when I say our, I mean myself. I spend a lot of time where people send me their telescope and camera specs or model numbers, and I figure out what they need, and I send them a little video back and show them why. And the software, this is my software. There you can see the URL. RSpec stands for real-time spectroscopy. This is some of the software I also spoke about earlier. Great software, really powerful. These people are my friends. I'll tell you, if for no other reason, once we start traveling again, hopefully in the next year or so, go to southern France to the spectroscopy star party. It's in Provence near the OHP observatory, at the OHP observatory. My wife and I went some years ago. Man, southern France, and you have a reason to be there. It's not just to consume culture and croissants and wine. So it's a fun star party with several days worth of lectures. There is a fair amount of English spoken there, and you get to meet people like the authors of this. Great people. I'm friends with them now, and they do remarkable work. How do you identify features in a spectrum? Well, there's this really cool book, even if you're an armchair spectroscoper or an armchair astronomer. Look at that. There's a spectrum with call outs for different things. Even like for a knuckle dragger like me, it says, ionized nitrogen. I don't know what that means, but there's also text that explains what you're seeing, and it's written for us. It's not written for professionals. So this is a great book, even if you're never going to do any of this. If you want to try it, even if you never plan to do it outside, software is free for 30 days on our site. 4 years ago, I did an hour-long workshop for about 100 AAVSO members in person at the SAS conference in LA. It was a great workshop. They all had their laptops with sample data. That was recorded. And the sample data is also on my site, as well as a link to the YouTube video. So tomorrow morning, you can get up, download the software, the sample spectra, follow along on that video, hopefully on a second monitor. It makes it easy. And at the end of an hour or two, you'd have spectra in your bones. Then when you read things about spectra, you'd really have a much more gut feel for what they were talking about. There are opportunities to do professional amateur collaboration. As I mentioned on the previous slide, the AVSO is really jumping into the spectroscopy. Stella Kafka, a great director now, and Arnie before her. Professionals, they know the importance of spectroscopy, and they're really promoting it quite actively. Oh, I know how it got so late, because you didn't let me start at 7 o'clock like I thought I was going to. I don't feel so bad. I guess I can slow down, maybe turn down the fire hose for a moment for these last 2 or 3 slides. So these are all amateurs. Christian Bull, you may have heard of, because in the 90s, he pioneered CCD spectroscopy. He didn't write the cookbook book on CCDs, but he's now doing spectroscopy, and just a brilliant guy, the benefit of which really happens every day. This is a professional at the University of Colorado. There aren't as many pro-am collaborations today as we'd like. There's more coming on board. AVSO has a Spectra database now, similar to the one that the UK has at the BAA, and one in France. I spoke to about 400 AVSO attendees at an open Zoom conference in August. There's going to be another one coming up in November. You can look at their site for that. Some of what you'll see in that will be things you've heard tonight. We've come a long way in the last, 45 minutes or so, 55 minutes. We've also come a long way in the last 200 years or 300 years. When I go to the AAS conferences, and I always feel like Dennis the Menace standing at my booth, I'm surrounded by these Hubble researchers. And here I am with this $300 or $400 classroom device, because about 50% of the attendees are educators. But I get a really good reception there. I've actually, at some of those conferences, I put a laptop on the hood of my car and parked it right outside the portico at the event. And then as these pros come out the door, I'll say, it took a while to screw up the courage to do this. Hey, you want to look at the spectrum of Vega? And they're all going, yeah, okay, what do you got? And then they're going, wow, you can get that? Where's your and they're going, 6-inch telescope? You can get that? So it's fun. It's also fun to show the public. I'd like to thank you all tonight for inviting me, for smiling at least, if not even chuckling to yourself at some of my jokes. Thanks for the outreach that you do, which is the way we pay it forward and backward. We've all been very lucky to have the opportunities we've had, and it's a good way to pay it back, I think. I'm here until you tell me to leave, and I'm happy to answer questions that you may have. Thanks again. You'll need to unmute your mics if you want to talk.
I have a question, a comment and a question.
Great.
The comment is, I actually took part in the spectroscopy Zoom webinar at the end of August that you talked on the AAVSO, and the talk is on their website.
Yes.
So if people are interested, if you go to the AAVSO website and look up the spectroscopy section, the video of that presentation is there. But the question I had is, since I'm sort of like the outreach person for the club, and so I get all of the kits from Night Sky Network to do activities. And one of the recent ones that we got was this one from Big Astronomy. And there's this little, it's this spectrum treasure hunt thing, and it has this little thing on it, so you can look at the light. Yeah, and it has, it's just looking at different types of light and seeing what the spectrum looks like. But I'm wondering, besides just looking at lights with this, is there anything else that I could do with this to teach kids or adults about spectrum, the light spectrums, and just besides look at the incandescent light, look at the fluorescent light, I mean.
That's a really good question. You know, because I work with tons of teachers. It's been part of the real pleasure of all this. And teaching Spectra is hard. Again, in this moment, I'm not promoting my product, but I'll tell you the thing that works with, and I don't think you'll have an opportunity to do this, is with gas tubes, like this one I showed you back here, you get really clear, distinct spectra. And unfortunately, I mean, gas tubes are, you know, this is about $400 and gas tubes are going to be about $400. So it's not a cheap investment. Teachers can do it sometimes. But one thing that you could do is, you know, they make, this is solar eclipse glasses, but they make rainbow glasses from.
I think I have some of those around here somewhere too. Yeah.
They're about $1 a piece, and you know, depending on your commitment to sanitation, you could reuse them. I find these easier to use. You may have found students with that little thing. I don't know if you've worked with students. It's hard sometimes to see the spectrum. You've got to get something at an angle. In fact, when I'm at teaching conferences like the National Science Teachers Association and the AAPT, the physics conferences, my leading line when I'm you know, being the obnoxious guy in a booth trying to hook people, is as I'm talking to people and maybe I've got them slowed down for a minute, and actually they're standing and chatting, I'll say to them, how do you do spectroscopy today? And they'll go, oh, you know, we use the handheld foil. And then with as flat a tone and face as I can muster up, I will say, how's that working out for you? And they break into smiles like you just did. And literally I've seen people stand next to each other, you know, co-friends, and start bumping each other in the rib, because 90% of them will say, it doesn't work, you know? And the other 10%, I'm not sure they're being truthful. So it's hard to teach with a handheld device. I thought when you said, I saw your previous presentation and I have a question, Stephanie, I was like really scared you were going to say, and my question is, don't you have any other material, Tom?
Well, I was realizing that it was all the same stuff you had said before, but I wasn't going to mention that.
Fortunately, it's been what, 5-6 weeks, I suppose. So you don't realize just how all the same it is.
I didn't remember it all.
I've now, and I don't tell people this at the beginning because I don't want them to sort of degrade their appreciation of the talk to whatever degree they have an appreciation. I've now given this talk almost 300 times over the last 8 years. Wow. So I did rattle on really fast, sometimes a little too fast, I think. But anyway, it's sort of like when you go see a comedian one night, you really don't want to go see them the next night again, because all those sort of like impromptus, oh yeah, you know, that's not impromptu. That comedian rehearsed that line. These aren't rehearsed. And I try and throw new stuff in all the time just to keep myself awake. But anyway, thanks for your questions, Stephanie. If you have any others, feel free to jump in. Any other questions?
Yeah, I just got a quick comment.
Good.
I did a talk to an astronomy club with spectroscopy, and I wanted to demonstrate light pollution. And you can take one of these gratings in a camera and go around to these different types of lighting. It's real informative. You shoot, you know, low pressure sodium, high pressure sodium, make mercury vapor, fluorescent, and look at the lines and where they appear on the spectrum. And it's really educational. You can see why LEDs, especially the blue ones, not so good for astronomers. Low pressure sodium was wonderful. It had a couple of big lines, those yellow sodium lines. That was it. The whole rest of the spectrum was dark. Real easy to filter out, and you know, you get a nice dark sky. Yeah,
that's true. In fact, I mean, unfortunately, it requires the camera and the technique and stuff. But if you have those skills in the audience that you can keep quiet for a few minutes, that's a cool activity. You know, my goal when I'm teaching most students, unless they're in AP Chem, Physics, or Astronomy is a little bit different, is if I can get them to come away and say that we can tell the temperature of stars by their color. I mean, that's one of the NGSS, you know, teaching points. Or to say something about how we can tell what a star is made of by looking at its rainbow. I mean, the bar is pretty low with those goals, but that at first blush, that's really sometimes the best that we can do. I've always hoped, and I never really pursued it. I always hoped I could put together a unit that would be a dry lab for students, but we would show, I thought it would really just be just eaten up by educators if we could show some of the CO2 in the atmosphere, you know, even with satellite images where you have some, you know, satellite image of CO2 measurements, but it's a spectrum. And somehow the spectrum is the secondary piece. The primary piece is we're measuring CO2 here. It's science. We know it's there. Because those would really fit well with science curriculum. Any other questions, comments?
You pointed out a difference when the grating is in front of the optical path or behind. What? Yeah. And I kind of lost that. What is the difference?
The difference is, I mean, first problem is it's just a camera, so it's not a cooled sensor, and it's a small aperture. Three inches is a little small to do much with many stars. It can be done though. The difference is that if you put it in front of the lens, if I had a camera here, it makes for a little bit more visual. But if you put it in front of the lens, the light goes through the grating is parallel, right? It's just arriving at the camera. Whereas if you put it in the, back in here with another adapter we sell on a T-ring, then it's in the converging beam because it's going through the lens in the camera. Yeah. And then that introduces some optical problems, which limits your resolution. Okay. So we have an online forum that's fun to peruse if you're curious about that. And there's some examples there of some really high resolution spectra and a lot of interesting discussion by people who, like me, love to help anybody who's interested in the field. But with a $40 adapter and a star analyzer, you can set this up, especially if you have tracking, and do some pretty interesting imaging with static images. They don't have to be raw images. They don't even have to be great images, but you do need to be able to track. Other question? Did that answer your question, Nick?
Yes.
Good. Thanks for asking it. Other questions?
Tom, I got a question.
Great.
Is that grating sold at most of your national astronomy outlets?
No, it's not sold in a couple people sell it, but they buy it from us. And we sell it directly so we can support it. Typically, if you call any of those outlets, I mean, as I mentioned, there's some decisions you have to make involving your camera and your telescope's focal length. That's where our calculator on our site helps, or where you just email me and say, tell me what I need, here's my setup. So I sell them directly from here.
Oh, okay.
You can buy them online at OPT and Farah at River something. I forget her name. I was about to compliment her. I mean, in fact, have any of you been to the astronomy show that was down in LA for some years? So it was a cool show, but anyway, if none of you have been there, then the story isn't all that interesting. What else? David, I love your setup there. That looks like a rocket instead of a telescope. I think you're in the wrong meeting tonight. What else? Any other questions?
I had a question.
Oh, good, Chris. What's up?
I was wondering, when you're doing spectroscopy on like far away objects that are influenced by gravitational lensing, how that affects maybe the spectroscopy?
I don't know. That's a good question. I was
kind of wondering if that affects like the red shift or the blue shift, so things look different.
I don't think they'd look that different. I don't know if there's any shift because of the gravitational lensing. I suppose there could be, but this is where you see an example of the river being shallow. That's something you would ask in our forum. It would be an interesting answer. The reason I'm looking over at my other screen is I thought I'd share my screen for one more moment, just to show you. This is I don't know what screen I'm sharing. It's this one. Are you seeing that that image of me?
Yeah.
Yes? Oh, okay, thanks. It's funny, Zoom isn't letting me know that.
No, we're seeing your website.
Okay, that's good. Thanks. Thank you, Stephanie. That's exactly what I wanted to show. I wanted to show here samples just if you're curious to do a little bit more reading, you'll see some of the examples I showed, and you'll see others. What made me think of this, I mean, there's the quasar I showed with a little write-up. Oh, I know. More interesting than this is, let me switch screens again. Because I think, you know, even ignoring spectroscopy, you'll find this interesting. So this is, if you do any solar outreach with a LUNT or, you know, some of the other telescopes, the PST, this is a great tool to augment that. It's a low tech, it's easy to use, and it again occupies your audience while they're queued up to see through your hydrogen alpha. This is a device, you can see a lever, and I'll show you a really crummy video of it here. A lever to tune it. This is a high resolution spectrometer, so you can only look at a small window in the spectrum at a time. So let's play this video. It's so Mickey Mouse, I'm embarrassed to show it. But there's the lever, and you can see that you can, you know, tune it. Right now, we're looking at the region where the magnesium triplet is, where there's 3 lines from magnesium for reasons I don't know. They have something to do with quantum mechanics. Let's see what that looks like. So we're now looking through the eyepiece, and we'll look at the lines. This is obviously a really awful presentation this way. There's the magnesium triplet in the green. Now, what I'm going to do in this video as I'm talking and moving the camera, unfortunately, around, is I'm going to move that lever so you can see other lines. So here's a hydrogen alpha line right there. And then we'll just see one more line here, and that is the sodium doublet on the sun. So I didn't actually mean to stop that, but so this is a really cool thing that, especially during the daytime, you could, and this is by Shellac that make higher end slit spectrometers. This is a slit spectrometer. You don't need tracking. It's got a gnomon here. You just point it vaguely towards the sun, and you're good for quite a bit of time. You could have, you know, a fold-out version of my poster, and you could run a little mini class. So Stephanie, this might be something you think about doing. The problem is that it really isn't cheap. You would buy this at OPT or maybe a little less expensively from France itself. You can do that shopping and determine from Shellac, from their site. That is actually an SH there, like the constellation.
There's what would you suggest? I have a PST. Is there something that could be attached to a PST?
I wish there was, but in fact, we need white light because a lot of these lines aren't the hydrogen alpha lines. It's a really good question.
That makes sense.
But you know, all of us, including myself, go down that track first until we make that connection. This is about $1,200 or $1,300. I'm really sorry to say, and plus a cheap tripod you probably have around already. But it would really be effective for outreach. If you have a PST here, I mean, it doesn't really show. I mean, you can pivot to hydrogen alpha with that little lever, but it's not exactly what you're showing them with the PST. But it's something to discuss. And the colors are just gorgeous as you move that lever, and you can let them move the lever. As you move that lever, you just see the whole range of the continuum, Roy G. Biv continuum go by, and they're really pretty colors. I mean, and the slow, gradual transitions. So that's something you can look at doing. Now, the other thing to quickly show you is this video here. This is a more advanced topic. This is Albireo A and B with a mono camera. Sorry, I'm not looking at my camera. I've got this on the different monitor. And this is the dimmer of the two, and you can see above it the brighter of the two. And they are different temperature stars. So my software is doing something we didn't talk about, and if you encourage me, I will, but I won't get into much of the detail. The curve of these plots in my software or with any software isn't going to be a Planck temperature curve until you correct it for the fact that your camera isn't linear, right? It's not nearly as sensitive in the ultraviolet and violet as it is in the green. So it has to be corrected, and the software is doing that on the fly here. So we're looking at one of the stars here. I'm going to play the video a little bit. This is Albireo B, which is a really hot star. Notice most of the energy is over here in the blue hot end of the spectrum. Now let's look at the other star. Albireo A is a really cool star, so most of its energy is in the red end of the spectrum. So on the fly, under the stars, this isn't something for outreach because it's pretty technical. Could be for a high school though. You can show by just dragging the sampling region between those two temperature stars, you can show how the curve shape differs, the Planck-like curve of the star. Professionals don't use the shape of the curve, the Planck curve. What they use is the existence of features. One final thing to show you, and that is, let me move this over to the screen we're looking at. Instead of showing you this video, I'm going to pause that. I'm going to pop up on a different curve. Well, I just closed that, which is, let me close it on another monitor. Oh, now, there we go. On a different curve, I'm going to show you a reference library. So this is a professional reference library of all the stars and subtypes in OB and FG KM order. And I'm going to pop one up here, an O star. Look how all of its energy, most of its energy is down here, way outside the visual region. But as you know, as you go through the star temperatures, through the types that Annie Jump Cannon and her computers figured out, this temperature peak migrates to the right, to the cooler reds. And I'm going to show you that by clicking an animate button. And I'm going to call out, watch how this peak moves to the right as we get into the cooler stars. So there's the B stars, A stars, F stars, G stars, K stars, and M stars. So we've just seen that the temperature curve of a star changes as we get into the different star types. That can be a cool demo, again, probably a little more than what you want to show to a bunch of students, entry-level students. But notice that the type A05 star, which is what Vega is, has deep professionally shaped dips right where my data is. It's pretty exciting when your data matches up with the professionals. Okay, I just took more time than I intended to showing you that. I'll stop sharing. That talks a little bit about star temperature and some of the outreach tools you might use during the day. I'm sort of a daytime observer mostly these days because I like to get a full night's sleep. And I live in Seattle and don't have the money to buy a remote telescope in New Mexico. Chris, I love your background, by the way. It's a great background there. In fact, just today, I need, this is not part of a script, I need your help here. This is a Sato voice. And that is, look at that background. Now, she looked at that today and she said, if you have people looking at that, I do have, strategically placed, that's actually some sort of nebula. But in general, it's a mess, right? And she said, look at some of the beautiful backgrounds people have. Chris, you're hurting me here. You really are.
One of my students had that same background on today during my astronomy class.
Oh, that's really sweet and a fantastic sign that they really like you, that they're willing to go to the trouble to find that. That's really very, very nice. I said to her, this is a effing badge of honor, right? It's like, and the same thing happened 3 weeks ago. I had my telescope sitting in the living room next to our deck door. We had some people coming for a safe sit on the deck. And she said, you've got to put that telescope away. And I said, why? She said, it's just messy. And I said, the people I really enjoy spending time with, they see a telescope disassembled in the living room. They're going, you go guy, go gal. So
yeah, I've got my telescope there. I've got my Saturn V. I've got my International Space Station, and I've got my astronaut pictures, and yeah.
Yeah, so now I can tell her that I got support from the meeting for this mess of a bookshelf. I'll tell you, this is a whiteboard. The question I didn't get tonight, but I often do, is do you have a Mac version? And we have a Mac version of a light version for school teachers for our gas tube spectroscopy. But then I tell people I'm working on migrating the rest of the features to the Mac. And then to prove that, I go over here and say, the good news is this is the features that still need to be migrated. The bad news is I can't erase these because they've been up for, I just checked to make sure I couldn't, because these have been up here for about 2 years. So they're like permanently, painted on the whiteboard. But having a whiteboard in your office, again, to me, that was the pinnacle. I mean, she mocked me for the longest time, but I think she realizes now that it brings me great pleasure. Anyway, other questions? All right, well, listen, all of you have a great night. I'm going to check out, go upstairs and get a little dinner. And thank you so much for for what you do. I really have a lot of admiration for the club down there. I've heard of you from a variety of sources over the years, so I was really tickled when you invited me to speak. Have a nice evening. Good luck imaging tonight, Mike, if you're going to go out. Thank you, Bob, for the applause, and have fun. I did tonight. I really did. Thanks for
Thank you, Tom.
Good night,
That was
everybody.
great.
Thank
Good.
you.
Thanks. That means a lot
Thank you
to
so
me.
much, Tom.
Good night.
As he mentioned it, I think it's still clear out there, so I may take a run at Mars. We'll see.
Now's the
But,
time
yes,
to do it.
Take
Couple years
advantage of
from now-
every opportunity you get to image.
Yeah, especially several years from now, you'll be kicking yourself if you don't.
Yes.
See you later.
Yeah.
Bye.
All right. Good night. Well, that concludes our meeting for October. That was very interesting. And I look forward to you in another month. And happy observing. Look at those Orionids and the planets. I mean, even if it's kind of a little smoky, the planets still hold up pretty well. So I encourage you to take a shot at the planets. All right, on that note, I'm going to end it here, and I will see you in a month's time. Good night, all.
Thanks.
Yeah.